Hello students, welcome you all in organic photochemistry. So in photochemistry, I will explain the photochemistry of alkenes and photochemistry of carbonyl compounds in detail. So before going to that, I should give you the introduction of photochemistry. So in introduction, I will tell you what is photochemistry, what is the difference between photochemical reaction and thermal reaction, then some of the laws which governs the photochemistry, for example, Grothus Drapper law, StarkEinstein law, which is also called as the law of photochemical equivalence. Then I will tell you the Lambert's law, then this Franck Condon principle that I will tell you. And after that, I will explain the Jablonski diagram, one of the important diagram in to understand this photochemistry, and some of the ways of energy transfer. We will also see the energy transfer process. Then we will come on the photochemistry of alkenes and photochemistry of carbonyl compound. So in introduction, if you see this photochemistry, it is the interaction of light takes place with matter. Interaction of light with matter. Okay. So usually means here we are discussing only this organic molecule. So we are concerned with the organic molecule over here. Light that we use is UV visible light, and this UV visible light having the wavelength 200 nanometer to around approximate range 200 nanometer to 800 nanometer. Okay, so light interact with the molecule, and after interaction it will undergo activation. So whereas in thermal reaction we use the heat is used to excite the molecule or to make it activate. Okay, so if we have suppose a reactant molecule, and if we irradiate this reactant molecule with light, then it will go to the excited state, and this excited state that would now be converted into some intermediate would be formed, and after this formation of intermediate, the product, we will get the product. So this is the excited state and this is ground state. It is the intermediate, and usually in photochemistry we will see the free radical intermediates are formed. Free radical intermediates are the most common intermediates which are formed in the photochemistry. And sometimes what happens, this excited state in this molecule, it may undergo deactivation. Deactivation may also takes place. Deactivation may occur, and if deactivation occur, then no doubt the yield of the reaction that will be low. Okay, so now some of the examples either in daily life or usually in where this photochemistry is used, like this photosynthesis is the most common example, and which takes place in plant uses light to synthesize its food, you can say. Then photoluminescence in firefly, it is also one of the common example. And then photochromism, this is the another word, photochromism. If we have seen the color of glass changes in presence of sunlight, and as soon as we remove the sunlight, then color of the glass comes to its natural color. So photochromism, the change in the color of glass, change in the color of glass, and as soon as we remove this light, the color will become the same natural color. Then phototropism is the next phenomena, and phototropism, it is the interaction, it is the orientation of some plants are there which orient themselves towards the sunlight. Okay, for example, the sunflower. So this is one of the photochemical process. This is the orientation of plant towards the sunlight. Towards sunlight, for example, if you see the sunflower is the example. Then photography, it also photography, and then some treatment of jaundice, usually in a newborn baby. Sometimes jaundice, they suffers from jaundice, so they are suggested to take sunlight. So treatment of jaundice, treatment of jaundice in newborn baby. And then like photo degradation of polymers, So these are few examples of this photochemistry. Now, so what is the difference between photochemical reaction and the thermal reaction? So let us see. Now, if we have, suppose, photochemical reaction and thermal reactions, what are the main difference between this photochemical reaction and thermal reaction? So here in photochemical reaction, this light is used, and here heat is used. Simple. We use the heat. Heat is used to activate the molecule. Is used to activate the molecule. Here heat is used to activate the molecule, that we can write. Now next, activated, here the activated molecule, it goes to the from ground electronic state, it goes to the next higher excited electronic state. Whereas in thermal reaction, after getting the energy, activated molecule undergo collision, and after it may go to the some other from ground translational rotational vibrational state to the excited translational rotational vibrational state. So here activated molecule goes from ground state, ground, or we can say ground electronic state, ground electronic state to excited electronic state. Electronic state. Okay. So, but here this activated molecule undergo collision. Collisions, and they go from ground translational vibrational and rotational state to ground translational vibrational and rotational state to excited translational rotational and vibrational state. Okay. Now, so another difference here, after excitation means in this case in photochemistry, in photochemical reaction, after excitation the electron go from bonding orbital to the anti-bonding orbital. So electrons go from bonding molecular orbital to anti-bonding molecular orbital. Here the electron remains in bonding molecular orbital, usually. Okay, so here if you see, this is usually spontaneous. This process is spontaneous, and this one is non-spontaneous, and that's why the Gibbs free energy may be greater than 0, means in positive. Here this Gibbs free energy, it means that should be negative here. Okay, so next here the rate of reaction, it depends upon the intensity of light. So rate of reaction depends upon the intensity of light. Whereas here if you see, the rate depends upon the heat energy given. Okay, so these are some differences between the photochemical reaction and thermal reaction. Now, so there are some laws which governs this photochemical reaction. So let us see some laws which governs the photochemical reaction. So one of the law, suppose if you want to understand it by diagram, this photochemistry, suppose, and this thermal and photochemical reaction, then how can you understand? Suppose if we have a reactant, and after absorbing the light, it will go into the excited state like this. So this is excited reactant molecule. Okay, now this excited molecule, it will now go into the intermediate state. This will go into the intermediate state, and from this intermediate state it will form some product, and product having the energy. Whereas now, so this is the energy of, you can say, this is the energy of activation that we have here. Whereas in thermal reaction, if you will see, then after absorbing the heat, it go into the excited state, and it undergo excitation, or it acquires some energy, minimum energy, and which is called as the activation energy. And now, so after acquiring this minimum energy, so this is the minimum energy of activation, you can say, and after acquiring this activation energy, it get transformed into some transition state are formed, and then this transition state, then it gives rise to the product. So like this we can differentiate this photochemical reaction and the thermal reaction. Now, what are the laws which governs the photochemistry? So some of the laws which governs the photochemistry, one of the laws governing photochemistry. So one of the law is Grothus Drapper law. Law name is, it is given by Grothus Drapper law, and this law was given in early 1800, like from up to this 1847, this law was given. Okay, Grothus and Drapper, they were two scientists and they gave this law. So according to this law, on the absorbed radiation, only the absorbed radiation only absorbed radiation produces the photochemical change, is effective in producing the photochemical change. So suppose if any molecule is there and if we irradiate light, then some of the light will get absorbed, and it is also possible that some light may get reflected or some light may get transmitted. So only absorbed radiation is responsible for producing the photochemical change. Reflected and transmitted radiation are not responsible for photochemical change. So this is simple. This is a very simple statement. So only what this law tells, only absorbed radiations are responsible for producing photochemical changes. It means, or what we can say means, reflected and transmitted radiation are not responsible for any photochemical change. So, or we can say reflected and transmitted radiations does not produce any photochemical change, does not produce any photochemical change. Does not produce any photochemical change. So how can we know that what amount of light, what should be the wavelength of light that should fall on the molecule so that it may produce any photochemical change? So nowadays we can easily find out by UV visible spectrophotometer. So by UV visible spectrophotometer we can determine the lambda max for any molecule, means wavelength which is absorbed by the molecule. So first of all, what we may do, first we can take the UV visible spectra of any molecule, and suppose if we take the UV visible spectra of any molecule between this absorbance and lambda max, and then what we got one of the spectra. Suppose this is the spectra that we got and this is the lambda max. So this is the absorbed radiation. This is the absorbed radiation by the molecule. And if we fall, suppose this is of 220 nanometer. If we if we irradiate any molecule, if we irradiate that molecule with light of wavelength 220 nanometer, then there must be some photochemical change that we can see. Okay, so we can determine the absorbed light by the UV visible spectrophotometer. Now, so this is a simple law. So second one is the StarkEinstein law. Einstein law. So according to this law, what this law tells? This law tells one molecule absorbs only one quanta or one photon of light. Okay, one molecule cannot absorb two photon of light or two quanta of light. So this is also a very simple law, but it has a lot of meaning. So one molecule absorbs only one quanta of light for getting excited. Okay, so this is the law, or it is also known as the law of photochemical equivalence. Photochemical equivalence. So according to this law, what this law tells? This law tells one molecule absorbs only one quanta of light, only one photon we can say, or one quanta of light for getting excited, So to excite the molecule, if molecule is get excited, it means if one molecule is excited, it means it has absorbed only one photon of light. If two molecules is excited, it means two molecules has absorbed two photon of light, and so on. So suppose if we have one molecule, then it will absorb only one photon of light for getting excited to this star. So, but one of the exception here, if we use a laser light, in case of laser light, one molecule can also absorb two quanta of light in case of this laser light. So this is the exception. So exception is here. So where the one molecule can also absorb two photon of light for getting excited. Okay. So, but one thing that should be noted here, that it doesn't mean that the excited molecule will produce any photochemical change. It is possible that excited molecule doesn't produce any photochemical change. And it is also possible that single excited molecule give rise to the more than one product, and that is the case for the chain reaction. So what is the main important that this law is only limited for the excitation of molecule. It is not necessary that excited molecule is giving any product. So one important note is this law is limited only for the molecule to be excited, for molecule to be excited. Okay, that is, it doesn't mean that excited molecule produces photochemical change. That is, excited molecule may not produce photochemical change, or we can say it excited molecule may not react finally. It is possible that excited molecule may not react finally to give the product. Okay, so that's why we can say the yield of product. In that case, the yield of product may be high or low. So if excited molecule undergo chain reaction, then it may give rise to the yield may be very high. If excited molecule may get deactivated by any way, then the yield of the reaction may be low, and that is called as a quantum yield. So yield of this photochemical reaction, that is, for that we use the word that is quantum yield. The yield of photochemical reaction is determined, we assign it the term that is called as the quantum yield, and we denote it by phi. So this quantum yield, it may be high or low, depending whether the excited molecule has reacted completely or the excited molecule may not react completely. So this quantum yield is equal to what we write. This quantum yield, this is equal to number of molecule reacted or formed, or we can say formed, divided by total number of photon absorbed. Photon absorbed. Okay. So if number of photon absorbed is equal to the number of molecule reacted, it means in that case quantum yield should be 1. So quantum yield that may be 1 when if this and this, they both are same. Total number of photon absorbed, that is equal to the total number of molecule, that same number of molecule get reacted. And this quantum yield, it may be less. It may be less than 1. So when it will be less than 1? When total number of reacted molecules is less as compared to the total number of photon absorbed. And quantum yield may be very high. Quantum yield, it may be very high when in case of chain reaction. Okay, so we will discuss this quantum yield in detail later on. Now, so this is the second law, that is StarkEinstein law. And suppose if 1 mole of light is absorbed, and then that 1 mole of light, that is called as the Einstein. So 1 mole of light absorbed is equal to, so what is this 1 Einstein? 1 Einstein. 1 Einstein. So this is equal to 1 mole of light of photon absorbed. That is called as a 1 Einstein. Okay. And we know that this 1 mole of light absorbed, and then that is equal to, suppose it is your N, that is Avogadro number, H nu. This is the 1. This is our 1 Einstein. This is 1 Einstein. And Avogadro number means 6.023 into 10 to the power 23 multiplied by 6.6 multiplied by 10 to the power minus 34, 3 into 10 to the power minus 8, and this is your lambda in nanometer, because usually in spectrophotometer, if you see the lambda that we determine in terms of nanometer. So we should convert all into SI unit, and if we convert it, then in terms of nanometer, then we should -9. Okay, so if lambda is equal to, suppose, 230 nanometer, then what we should write over here? We should write 230 into 10 to the power minus 9 meter. So this lambda, that should be converted into this one, and this is equal to this 1196 divided by lambda kilojoule per mole, this figure. Okay, so now, so this is about the Grothus Drapper law and StarkEinstein law. Next law, I will tell you this next law in brief about the next law is the Beers-Lambert law. Beers-Lambert's law, and according to this law, we can write the Beers and Lambert's law separately, or we can write in a combined way. Now, according to the Beers law, we write Beers law. Then what we write? Now, suppose if we want to find the UV visible spectra of any solution that is containing any solute, then we put that solution in a sample cell, and we keep this sample cell in a UV visible spectrophotometer. And suppose this is a sample cell, and this sample cell is made up of quartz. This is made up of quartz, and it is called as a quartz cuvette. And suppose this quartz cuvette contains a sample solution having the concentration C, and the length of this sample cell is, suppose this is the total length, is suppose B, and suppose a beam of monochromatic light or incident light falls on it, having the intensity of that incident light is I0, and the intensity of transmitted light is suppose I. Then what would be the intensity of absorbed light? intensity of incident light minus the light which is transmitted out. Okay, so the intensity of absorbed light, that would be is I naught minus I. That would be the intensity of absorbed light. So according to this Beer's law, when a monochromatic light falls on any absorbing medium, then decrease in intensity of light with this decrease in intensity of light is directly proportional to the concentration. Whereas according to Lambert's law, the decrease in intensity of light with path length, the decrease in intensity of light is directly proportional to the path length. Suppose this path length, we write B is the path length, or suppose we write this L is the path length. So this is the Beer's and Lambert's law separately. Now, if we want to write the Beer's-Lambert law in a combined way, then how can we write? When a beam of monochromatic light falls on any absorbing medium, then the decrease in intensity of light, is directly proportional to the intensity of incident light and path length and concentration of solution. So this is the statement for the Beer's-Lambert law. When a beam of monochromatic light falls on any absorbing medium, then decrease in intensity of light is directly proportional to the intensity of incident light and concentration of solution. So mathematically we can write Di naught, okay, upon with path length is directly proportional to the intensity of light and concentration of absorbing medium. Okay, so this is the our statement for this Beer's-Lambert law. And now so suppose we want to integrate this. Then according to this, what we can write now, Di naught upon I0. This is equal to what we can write. Suppose proportionality constant, we take K and CdL. Okay, now let's integrate it from I is equal to I0 to I is equal to I, and this one from L is equal to 0 to L is equal to P, and suppose we write it N. What would be the, so this is equal to ln I naught upon ln, this is I, this is equal to P minus 0, and this is K, and this is C. So finally what we can write, this is equal to ln I0 upon I, this is equal to KCB. Now log to the base 10, if we take K divided by 2.303 CB. So what we can write finally, so this is equal to log of I naught upon I, this is equal to epsilon naught Cb, and this is equal to the absorbance, and this is the mathematical relation for this Beer's-Lambert law. And here this is A is called as the absorbance or optical density, absorbance, or we can say optical density, and here this I naught is the intensity of incident light, okay, and this I is the intensity of this transmitted light, and here this epsilon naught is the molar absorptivity coefficient, or we can say molar absorptivity coefficient, or it is also called as the extinction coefficient. This is also called as the extinction coefficient, and C is the molar concentration of the solution, and B is the your path length. This is B is the path length of sample cell. B is the path length of sample cell. Okay, so this is the mathematical relation. Now, from here, what we can write that actually the transmittance. What is the percentage transmittance? Transmittance, if we say this transmittance, this is equal to this I upon I0 would be the transmittance, and this percentage transmittance we can write the percentage T, that is transmittance. This would be equal to the, this is total light I0, I upon I0 multiplied by 100. And from here we can determine one of the relation, and suppose I take log of this percentage T, this is equal to, and this log of I0 upon I upon the I0 plus log of 100 is 2, and now this can be written as log of percentage T, this is equal to log I upon I0, this is minus A, this is minus A plus 2, and this A that we can write, this A is equal to, okay, so this A, this will be equal to 2 minus log of percentage T. So we can use it to solve few numerical problems. If percentage transmittance is given, then we can determine the absorbance from this formula. Directly we can use it. Okay, so this is about Beer's-Lambert law in a brief, and one of the this we can say a condition for this Beer's-Lambert law, the solution that we are using here, that should be dilute. It is not obeyed when a solution is in concentrated form, because in concentrated form some association of a solute molecule takes place, or the formation of complex takes place, and that will not give you the U visible spectra for the original solute molecule. Okay, so it is only applicable if your solution is a dilute one. Okay, so now next law is in photochemistry. The next law that I should tell you, Franck Condon principle. Now what this principle tells, so according to this, the statement, what this statement is, when suppose it is when electronic transition, or we can say the electronic transitions are so fast and rapid, that there is no appreciable change in the internuclear distance between the atom of the molecule. Okay, so let us understand this. What this principle tells: electronic transitions are very fast, and it is so much fast that in between that time there is no change in the internuclear distance between the atom of the molecule. Now, so how can we understand it? And we can understand it with the help of Morse curve. And we know that if we draw one of the Morse curve, and suppose this is our curve, and according to this Morse curve, suppose if we have any molecule, and suppose this is a molecule A and B, and this molecule, it has the internuclear distance between the atoms of the molecule is, suppose this is R, equivalent is the internuclear distance. And when it is in stable form, okay, then suppose the molecule lies over here, and this is the internuclear distance, suppose from A to B, okay, and this is our distance, and this is R equivalent, or we can say this is a bond length. Now, after absorbing the energy, what will happen? The molecule will undergo some vibration. So vibration in our vibration between the atoms of the molecule takes place, and suppose, and we can say that the bond length of the molecule that will may expand, and then it will come to its original position after some time. So after absorbing the energy, after absorbing the radiation, the molecule will the internuclear distance between the molecule will increase like this from here. Okay, it will increase, and now again it will relax back, and it will now decrease to here. Now if so, this is the, now it is expanded and then decrease, and this is the equivalent bond distance here. Now after absorbing more energy, little more energy, then again the bond length, we can say it expands, and then after expanding it will go here, then it compresses, it will come here. So next state, that would be next vibrational state. Suppose this is one vibrational state, this is 0, next vibrational state suppose 1, and again after absorbing more energy it will go over here, it will expand, then relax back to its position. So bond length, first it increases, and then after, when it relaxes back, it decreases. Okay, so suppose this state is vibrational state is 2, and now like this is 3, and so on. Okay, and after absorbing, suppose we give more and more energy, then what may happen? This may undergo dissociation, and this may be called as this dissociation energy. This may be called as the dissociation energy. Suppose this. So this is our ground electronic state. This is our ground electronic state, and we will present it by suppose E0. And suppose if we give more with a U visible energy, in that case, after absorbing so much of energy, the electron may go from ground electronic state to the next higher electronic state. So after absorbing the energy, now the electron may go to the next higher energy state, and this is suppose excited electronic state, and we write it by, suppose this is E dash, is the excited state. And here the molecule, again after going to the excited state, the molecule, the vibrational, now it will in excited state now, the suppose if we, this is the V0, this is a vibrational state, and suppose this is again a internuclear distance, this is the equilibrium distance in a, now the equilibrium distance will not change. According to this figure, the equilibrium distance will change from R equivalent to R dash equivalent. Okay, equilibrium distance will change from R equivalent to R dash equivalent. And now if some more energy, slight more energy is given, then the energy, the electron or the molecule will undergo in a next vibrational state, and suppose it write it V dash is equal to 0. Now some more energy, V dash is equal to 1, V dash is equal to 2, and these are the excited vibrational state corresponding to this excited electronic state. Okay. Now suppose a molecule here, the molecules are highly populated or at this place, then we may write like this. So, and again, and like this. Here also. So the transition, okay, so the transition, what we expect that electron go from ground after absorbing the UV visible light, electron go from ground electronic state to the higher excited electronic state, and it will go from here most probable region to the next probable region. Like this the electron will go. So this is expected one. This is the expected figure that we expect, means electron are going from here to the here, and during that time, during the electronic transition, the internuclear distance is changing, or what we can write here, this R dash equivalent is more than R equivalent. So we expect this much. So but what this Franck Condon says, according to this principle, he said that electronic transitions, these electronic transitions are so fast and rapid that there is no change in the internuclear distance between this. So what is the reason? That means this internuclear distance will not change. Okay, this internuclear distance will not change. So according to this one, what kind of figure that we may expect? The figure would be something like this. This is the ground. Okay, and this will be the excited one, excited electronic state. So this is E naught, this is E dash. Okay, and here are equivalent in ground electronic state, and after absorbing the energy, more energy, then electron will go into the excited level, and during this excitation, the internuclear distance will not change. Here in an electron, after going into the excited electronic state, you can see that internuclear distance is remaining same. R equivalent is the same internuclear distance. So this is the Franck Condon principle. This is our Franck Condon principle. Okay, so and what is the reason for this? So here we can say that internuclear distance between the atoms of the molecule, that doesn't change. So the reason for this is that the mass of the nucleus is so much higher in comparison to the mass of electron that the nucleus cannot move during the time when the electron get excited, and during that time the electron again relax back to its ground state. Okay, it could not change its position, the nuclear distance could not change, and during that time the electron relax back to its ground state. So reason is that the nucleus is around 1000 times heavier than that of electron. So the mass of nucleus is around 1000 times more than the mass of electron. So this is the reason. If mass of nucleus is so much high, then in that case it is not able to move from its one position to the another position, and during that period the electron first excite and come back to its original position. Okay, so this is about the Franck-Condon principle. Hope you are understood. Thank you.